Okay, welcome to 2018. We are recording, so just so you guys know. Let me share my screen with people on WebEx. So today we've got some new material to go over. There's an exam next week, just to remind you. Yep, remember? So what we're going to do today is do another homework together. I may give you some other problems to do over the weekend, but we'll wrap up most of the new material now. I'm not going to start a new chapter after today before the exam. This is the last time we'll see each other. So if you will let me give you homework problems, I'll make the exam simpler. That's the trade-off. What I am looking for in the exam is not to surprise you or you to do problems you've never thought about before, but rather to show me that you absorb the concepts. So if you can convince me you know the concepts, I'm much less concerned with whether the math is completely perfect and you have exactly the right number of bits and the milliseconds are perfect. If you make some math error when you're working an equation, but you use the right equation, that's worth almost all the points to me. Because that's the part you need to remember, that's what you need to learn, that's what you need to hold on to. You'll use Excel and tools like that your whole career. So you'll have help with the numbers part. What's important is that you know how to approach the problem. So for that reason, I'm kind of shifting a little bit and we'll look for you to do most of the work on the homeworks. And if you kept up with them and you kind of have the concepts, then the exam will be fine. You also can bring a sheet with you of anything you want on it. So if you go back through the material and there's formulas that you want to jot down or ones that you see today, you can transfer them onto a sheet. I will also try to give you a printed study guide a few days before the exam so you know exactly what's going to be on the exam. It will tell you the problems that will be there. I'll say things like, make sure you know how to calculate the maximum length of a network or how long it's going to take to broadcast or transmit a packet or what the difference is between persistent and non-persistent connections. I'll tell you those kinds of concepts that you need to know, okay? So it should be doable. So this is what happens when I don't get the homework done with you guys before the test. We'll rebalance it out that way, all right, to make it fair for you guys. Okay, so to that end, the first thing we need to cover is we've got some new material to go over, but we're going to do the homework for it at the same time. And the stuff is mostly we've talked about already, but we're going to use an animation tool to kind of help get things home. So on the Dropbox drive and on Blackboard, you will find this homework. There's a Microsoft Word version and a PDF just like last time. So if you want to download the document and type in answers as we go along, you're welcome to do that. Okay, and so we also have a recording in case you need to go over it later. All right, so there's a delay simulator. You know, there's lots of really good simulators that come in this book. And one of the problems that we've tried to solve with HTTP is this problem of state. So we've talked about it a little bit, but I want to make sure you guys understand what state is about. HTTP is a server that does not maintain any record of what's going on. It doesn't remember anything that it's done. If you show up again, it won't recognize you. It's just like a traffic light. You show up at the traffic light, you wait for it to turn green, you turn left. If you come back around the block, the traffic light's not going to recognize you and go, oh, you were just here a minute ago. It's not going to have any idea who you are. If you show up 1,000 times, it's going to do the same thing every time. It does not maintain state. A policeman will maintain state. They will notice if you show up like 6 times in a row at the same traffic light and they're standing there and they're like, pull over, what's going on? What are you doing here? My father maintains state. My father would always notice if someone drove by a little too slowly or twice, and then he would usually call the police on them. So he was like super vigilant. He was like the watch person in our neighborhood. And so it was a source of safety and constant humiliation for me. So my father at one point told me, that's my job, to be a source of constant embarrassment to you. And I'm like, I'll use that phrase with my kids. So I did. When I had a child, he said, Dad, you're embarrassing me. I said, that's my job, to be a constant course of humiliation in your life, and he's like, "Argh." So, and it's true though. That's what parents do. They just embarrass you all the time. So those, they will maintain state. HTTP and a traffic light will not maintain state. So there's a big problem that we have. It's twofold. Number one is there's lots of objects on a typical web page, and if we need to download lots of objects, we don't want the server to constantly close the connection every single time we want to get it. So in the beginning, it was okay. You would go grab a page, and on your way out the door, the server would close the TCP connection. And so when you needed to go back and get something else later, you would just reestablish a new connection. That's time-consuming, but very efficient, because the server is not reserving any resources for you. As soon as you're done, it releases the buffers, it kills off that process, and so it's good for the server. But things have changed. Now our web pages are horribly complicated, and I'll show you one of my favorites, the NewYorkTimes.com. How much do you want to bet that the top story is going to be Trump's speech last night? Trump will be on the front page of the New York Times. That's like saying the sun's going to come up. Trump's always on the front page of the New York Times. So here we go. You ready? So we'll type it in. So some things show up instantly, and some things take a little while to display. So you'll see objects are starting to show up. If I go down here to the clickbait, there's more stuff still building. But it's a massive page. There's at least 100 objects on this page. Every single one of these objects requires a connection to a web server. So when we started building pages like this, it became awful that it would slam the door and close the connection and release the buffers and do all of that, because this means I'd have to start 100 TCP connections. So it would take minutes to load the page. So we've changed what we do over the years. It's got some nice graphics in here as well. Who is this? Another pro football league is born? This is terrible, because now I want to read the, how much do you want to bet he was squeezing her arm like really hard? I'm teasing. Last night the president gave a really big speech, and so that's why everybody's kind of talking about it in the U.S. today. It was actually a good speech. He did a good job, which is very difficult for me to admit. Okay, so let's make some good points. All right, so back to this delay estimator. What we did to make this situation better was we switched from non-persistent connections to what are called persistent connections. And when you open up a TCP connection, one of the things you can do when you negotiate HTTP is you can ask for a keep alive variable to be set. And you can ask for a certain number of seconds. So what that does is alert the web server that you're going to be grabbing more objects from this same server, so please do not close the connection. Please leave it open. And if you use Wireshark to grab a page, you can see this happen. So we can try grabbing one to see if it works. The problem is it's lots of packets, so I don't know if it's gonna, I don't know if we're gonna be able to pull it off. So let's try it. Okay. Let me see. I don't really want to go to that site. Let's go here. I think this is the one I want. So let me start a Wireshark. And I'm going to try to go to a website that's not encrypted. So we're not using HTTPS. And so we should be able to read everything that's going on. We should be able to read what I'm trying to show you anyway, but just to be safe. Okay, we're there, and I'm going to hit return, and we're going to stop. So we've gotten Wireshark, and I need to turn off monitor mode. So I'll explain what that is later. Okay, so we're back to seeing what's here, and what I want to see are HTTP packets. See, this is the problem. It tries to show me stuff, but it's encrypted. I want to see if I can find one of these. And there's lots of TLS in here, which is encrypted versions of it. Let's see if I can get lucky. Because I'm running WebEx, there's just tons of other packets in here. And if I can't find it here, I'll go grab it from a Keep Alive example for you guys, because there's lots of PCAP files we can grab. So let me find one. I'll just Google one here. So Mozilla has a decent website with lots of good examples. So if you ever want to look for HTTP examples, it's the best place to go. They have like simple little tutorials. So had I grabbed the packet, and I don't know why it wasn't encrypted, I should have been able to get it, so I have to think about what happened. One of the things that you'll see when you negotiate a connection with the server, you will get an answer back. So this is a response from a server saying, I am able to speak HTTP 1.1 like you asked. 200 means I had the file that you requested. You asked me to keep the connection alive, and I agree I'll keep it alive for an enormously large time, 1,000 seconds. That's amazingly generous. You'll never see that. You'll always see smaller numbers. But if you don't ask me something at least every 5 seconds, I'm going to shut the door on you. So it's like, okay, well, are you really being that generous? Because that's really fast. So this is enough time to load the New York Times webpage, because the browser will automatically go and request all the objects. It will never wait 5 seconds in between. But if you and I were doing it, like if I was looking at the page and I was scrolling through and I click on something, it's very likely that 5 seconds has gone by and it will have closed the connection. So this doesn't make tons of sense. It would be better to say timeout is like 10 or 20 and the max is maybe 100. So the request, though, they didn't show in here. So the request, they didn't negotiate. That's okay. This is the response. It's the same variable. The other thing that they're showing us that's important here is they tell us the last time the file was changed that we're about to download. And the reason why this is very important is one of the other ways of speeding up downloading web pages is just to not download them, is to go to a copy of some of the objects that you grabbed earlier, or that maybe somebody else on your network grabbed earlier, and keep a little stockpile of those objects. Keep a cache. You have a cache on your own browser, right? So that's where your browser is going to keep copies of objects. And it's one of the reasons why when I opened up the New York Times page, I pointed out to you, you see how fast the object shows up, the New York Times logo? It's immediate because it's already on my hard drive because I opened this page yesterday. And when I downloaded the object, the New York Times told me it's okay to cache this object for 30 days or for 100 hours or for 15 minutes, whatever they want. And so anyone along the way that wants to keep a copy of it at the ISP or at Tech or on my browser, they can grab copies of those objects and store them. So that's happening all the time. So the other problem I have is I don't really know where the page is coming from. Parts of it I assume are coming from the New York Times, but I'd have to use Wireshark maybe to try and get a hint to see where the packets are actually coming back from. I know where I'm sending them, but it doesn't mean the response is coming from there. Because what the caches do is they will intercept me in the middle. Okay, so lots of problems we have to solve. We have lots of objects we want to get. We don't want a connection closing on us in the middle. So back over to this delay estimator, one of the things we can do is just start with the regular type of connection, a non-persistent connection. This is one that will grab objects one at a time. So there's no parallelism. It's set at 1. I can't change it. And I can pick however many objects I want, 1, 2, 3, or 4. So let's pick 4 objects, and let's look at what the transmission delay is. It can be, maybe half a round trip time. So what they've calculated for me already is that the total delay is going to be 12.5 round trip times. You'll find when we calculate these sometimes we don't bother with seconds or milliseconds. We'll just calculate it in round trip time. So what this is basically saying is I have 1, 2, 3, 4 objects and a base web page. So there's going to be 5 things I have to get. There's 4 objects on this page. Once I grab the page, so I have to grab the page first, and then I can see there's 4 objects on it, and I can go get them. And because this is a non-persistent connection, it's going to close the connection after every object. So here's what's going to happen. I'm going to negotiate a TCP handshake from my client to the web server. It's going to acknowledge back and say, yes, you have a connection. Then I'm going to ask for the HTML, the base page, like index.html, and it's going to send it back to me. And this line is thick because there's a lot on the page. So it takes a little while to transmit it. So the page will arrive. It's shown here as like a single packet, but that's okay. It's just a big one. And now I'm done. So I have my transmission delay here, which is why it doesn't show up as just a line. And now I need to inspect the page. I see that there are 4 objects on the page. And now I'm going to go and grab the 4 objects. So I have to negotiate another TCP handshake, ask for the object with an object request message, and get the object back. There's transmission delay to receive the whole thing because it's a big object, and it closes the connection. And I do it again and again and again. So this will work all day long. This will work. It's extremely slow. It also requires going to the traffic light over and over and over. Usually, this is a problem because the objects are on the same server that the page is on. So if you go back to the New York Times, again, it's a great example of this stuff, and I pull up my inspector, right here, oops. The nice thing about the inspector in this browser, it's kind of nice, is if you click on an object, it shows you in the HTML where it's requested. It's still loading the page, so it's struggling to finish loading the page. So it doesn't load it instantly the second time. And what I said about caches, you might think, well, don't you have a copy of the page now? Why are you having to go back and get all of this stuff? Well, you notice the URL? One of the URLs it's getting is Google Analytics. Google will always give you a fresh ad, so you're going to have to go to Google every time. And also, Google is not the NewYorkTimes.com, so I will not find that object on their website. What I will find when I go down to one of these links to like an image here, and this one's going to switch me to something else. I just wanted to, let's see if I can find an ad. There's lots of CDN stuff. I don't know if you guys can see gstatic.com. There's like crazy list of URLs. All those are on here. Okay, so I'm going to show you, right here is a URL, opengraphprotocol.org. That is not NewYorkTimes.com. So this is an object that I will have to go and open. I have no choice but to open a separate TCP connection. It's a different server. I'm not going to find the object. Here's one, contextual.media.net. Here on their website at VI Assets. That's on the same site as probably New York Times. Here's the New York Times URL specifically, Google Ad Manager, but this one is actually Google Tag Manager. Okay, that's kind of neat. Optimizely.com, cdn.optimizely.com, doubleclick.net. This is ridiculous. There's like 100 URLs on this page. Every time it's a different site, I'm going to have a different connection to get there. Right? So this assumes that they're all on the same site. And if I could convince the site to let me grab more than one object at a time, this would go faster. All right, so let's go to the homework and see what problem it is that we've been asked. Which common type always produces the greatest HTTP delay? Okay, well, we can look at a couple others before you make up your final decision, but this one's pretty bad. It's hard to imagine that it would be worse than this because it's a completely new connection for every single object. I mean, what are you going to have 2 connections for every object? How could it get worse than this? This is already bad. So let's try switching to the next one. Non-persistent connection, but with parallel connections. And let's do 2 connections now and see what that one looks like. Ah, much shorter. So what's happening here? You can't see it on the graph, so I'll have to draw it for you. But what's happening here is I have one TCP connection to get the HTML page. So this is the handshake, which is what we call the first negotiation that TCP does, to ask permission to talk. Now that you have a connection, you can ask for the HTML page. The protocol you will speak is HTTP, but you're using that protocol to grab this index.html file. Once you have it, there's still 4 objects. That did not change up here. Still 4, but I have 2 parallel connections. So what's happening is I'm getting object number 1 here at the same time. I'm requesting object number 2. They're happening on top of each other, so it looks like one. And then when those are done, presumably they finish at the same time, close enough, it doesn't mess up my graph, I ask for object request 3 and 4. So elapsed time goes down the page, as you remember. So I've been able to do the objects in half the time. It didn't change the TCP connection, and I left some detail out here as well, just to try to show you what's going on, because it's still non-persistent. So after I grab the HTML page, I still have to negotiate a separate TCP connection. I'm just going to negotiate 2 at the same time. One for object 1, one for object 2, and then I'm going to grab object 1 with the first connection and grab object 2 with the second connection. And then they close. And then I'm going to negotiate, salute, 2 more TCP connections in parallel. And those are for object 3 and 4. And with the connection number 3, I will grab object number 3. And with connection, so it's still 4 TCP connections for the object and a 5th TCP connection. There's no change in the number of TCP handshakes, and there's no change in the amount of work that's done. It's the same total number of bytes transmitted between the server and the client, but we just do them slightly in parallel. Right? Make sense? Okay, so this one is more efficient, right? This one is finishes sooner. I will see my web page a little bit quicker. And if I come up and make it 4 parallel connections, then it looks even better. Same total amount of work. Don't get fooled by that. This is not just one TCP connection and one object. I'm still grabbing all 4 objects. I'm just doing the things in parallel. So that's one improvement. Let's go back to one connection and switch to the next one. You ready for the next one? We haven't done that yet, but there's a way to do that. This one's grabbing 4 objects, 1 each per TCP connection, and I'm just doing 2 TCP connections at the same time. So I'm telling my software to spawn off 2 sockets, open up 2 TCP connections with 2 different port numbers going both to port 80 at the other side. It negotiates as if there are 2 computers showing up. The server has no idea they're both from the same computer. It doesn't care. It doesn't maintain state. It doesn't know that you and your sister are now in cars next to each other at the traffic light instead of being behind each other. It doesn't care. It doesn't know. It's the same amount of work. Okay, so we're going to go to the next one, which is persistent connections. So this is what we want. We do not want it to hang up. This is the keep alive request. Please do not shut the connection. Please keep it alive for me for so many seconds. And what we saw was the response back. So we'll do this the simple way first. We didn't give it a name at the beginning. We now call it without pipelining, but here's the way this looks. So we open one TCP connection. We ask for the HTML page. Presumably in this HTTP transfer, in which we ask for the HTML page, we are also asking for a persistent connection. We are also requesting of the server that it keep the connection open. Does that make sense? Yep. All right. So I'm going to keep it open. I'll grab the HTML. I immediately inspect it. I see there are 4 objects on the page. And so I start sending the request to the objects. I do not need another TCP connection in here. It's still open. What's not shown here, which would probably really happen, is there'd probably be a little gap. So let me show you what that would look like, because the computer isn't instantaneous. So I'll send my TCP connection, my handshake. I will, TCP has already been given the HTTP message to send. And we need to come back and talk about that. So let me switch colors so I don't forget to mention that. We need to talk about how the server knows to open a TCP connection. So here is an HTTP message, and I'm using it to request an HTML page. So I'm basically using a GET message to get an HTML page. That's the syntax of the HTTP command that I will find inside the packet. All right, so now I've got it. What they're not showing that's probably going to happen, and they said this page was kind of big, so it required some transmission time. That's okay. There's probably going to be a delay here, while your browser takes a moment to figure out what it wants to do next. It will parse the page. It will see that it has 4 objects. It will look at the 4 URLs. It will build HTTP GET messages for each of those. It will handle the TCP. TCP will wait in line and put them onto the network. But that's going to take a moment. So there's usually going to be a little gap here that they don't bother showing. So what I'm going to do at this point is send another GET message. So I'm going to do another HTTP message. All of my exchanges are HTTP commands. This one's going to be a GET message for whatever the object is, probably a JPEG image, something like that. It's going to be object 1, and the object is big, so it takes a moment to transmit it back. So the first bit shows up here. The last bit shows up at my site over here. There's probably no delay at that point, so you'll just continue on. So what's missing from this diagram that I had on the non-persistent connections? So I have the request, right? And do I still have the same number of requests, same number of objects? There's no handshakes. Only one at the beginning, right? Only one TCP handshake. So if this is, I don't know, half a second, you've gotten rid of 1, 2, 3, 4. You've sped loading your page up by 2 seconds. And the whole page only took 1/2, 1, 1.5, 2, 2.5, 3 now, so it took 5 to begin with. So it's a very substantial reduction in time, 40% reduction roughly in the amount of time it takes to load a page. Would you like your pages to load twice as fast? Yeah, so that's what it'll do, right? But wait, there's more. Download now and receive absolutely free parallelism. So the last one, so is this one faster than the first one we did? A little bit, right? All right, so the last option on here is persistent connections with pipelining. So with pipelining, we can choose, like we did before, how many things are done at the same time. But this one is going to automatically try and do as much in parallel as possible. It's not letting me choose how many parallel connections I've got. So it will just max out whatever the browser's got. And the browser will have a restriction from the operating system for how many simultaneous TCP connections it can open to the same destination and how many it can open in total. And the operating system will have an overall total as well, so you may not get any if everyone else is hogging them all up. So this is intensive. And so whenever you see that we are trying to ration the number of TCP connections you have, you should immediately think, if you are going to survive life on the internet, you should immediately think, how could that be bad? Because I guarantee you there's lots of other people who are thinking exactly that, always. How can I attack you? How can I hack you? How can I use this to my advantage? So when I see that the server and the browser are trying to limit or ration my resources, in this case by maybe not allowing me to have 100 parallel connections, then that tells me having 100 parallel connections probably would crash the system then. Or else they let me do it. Why wouldn't they let me do it? The network can handle it. It's the internet. Why would it not let me? So indeed, this is an attack vector. One of the tricks that people will use is they will send half requests to a site and not finish getting the rest of the object. And the server, or they'll ask for lots of keep alives with lots of connections. They'll ask for connection to be kept alive for 1,000 seconds, and they'll hope that the server says just okay, and not say what we saw a minute ago, which is, I'll do it, but you better ask me something in 5 seconds. That's really important to have a number that you can manage, because if you don't, you're going to be reserving buffer space, TCP resources, sockets, memory, operating systems, responding off processes for someone who has no intention of ever coming back. So what are they going to do? They'll open 100,000 of these things in 2 seconds. And they'll just send you 100,000 things, TCP, handshake, keep alive, get messages. And they'll just ask you to keep it alive. And you will, and you'll crash. Or you'll deny service from someone else. Right? So anytime you see limiting taking place, it's kind of sad to have to tell you this, but be paranoid. Right? Be paranoid. It's like seeing, you know, $1 on the table. First you're excited, and then you're like, wait a minute, how did that get there? So I have to tell you, I'm super paranoid after all these decades in the business, and I'm really worried about it. So I try to be very conscious that I'm paranoid, like what can go wrong. But it served me really, really well, because if you can anticipate some of the things, then you don't get burned as often. Okay, so back over to the delay estimator. So this one was persistent connections. How can you tell that it's persistent connections? Yeah, in fact, there's only one TCP handshake, and if the only thing I had done is grabbed a blank HTML page that all it had was text and it didn't have any objects on it at all, then this thing would have ended, you know, right here. The object request wouldn't have been there. There would have been no object to request. But there was an object. It's on the graph. Therefore, I notice that there's no second TCP handshake, so this must be a persistent connection. Okay, is it possible to ever have a situation where I take a look at what's going on in the middle of a transmission, and I know some things have happened before me, but I showed up late, and I just turned on Wireshark, and I'm just now observing what happened, and the first thing I see is an HTML page request and an object request after that. And I'm trying to figure out, I know it's persistent because there's no TCP handshake here. But what I don't know is, was there a TCP handshake here? So my question is, does there have to be a TCP handshake before every HTML file? So let's walk through an example, and let's see if we can figure it out. Here's the New York Times. Right, I'm on their webpage, and I'm coming down bluekai.com. That's not on their website, right? It's a different computer on the internet. If I click on this link on this web page, am I going to need another TCP connection? It's a new computer. I don't have a connection to it. Yes, I will need another TCP connection. What about if I click on doubleclick.net? Yes. Google.com? Yes. Let me pull one up here. I know there was one. I saw it a minute ago. Here we go, NewYorkTimes.com. Where did this overall page come from that I'm looking at currently? NewYorkTimes.com. Here's a link on that page to another URL, also at NewYorkTimes.com. Do I require another TCP connection? I would hope I don't, you do have to have a connection open, but if you've clicked fast enough, it hasn't shut it down, and you asked for a persistent one to begin with, you'll be lucky. It'll still be open, and you should be able to do it again. You can see that with Wireshark. You can just look for TCP connections. The handshakes are packets. You can see them. So what I would like to do is find where this is on this page. Any one I can. Okay, here's a link. So I'm going to start up Wireshark again. Oh my gosh, I was grabbing packets the whole time. Are you kidding? That must be like 100,000 packets. I can't believe it worked. That's bad. Okay. All right, so let's see. So the content of the web page will be encrypted, right? Because it's HTTPS, but just establishing TCP shouldn't be. TCP has no encryption. It's also not an application. It's a transport layer protocol. So I should be able to see it. Let's see if we get lucky. So here I'm starting it, and now I'm going to go to here, and I'm going to go back, and oh my gosh. And let me see if I can see. This is also one. That's another URL. Let's see if that pulls it up. And I'm going to stop. Okay. So what I want to do is sort by protocol. That was already 11,000 packets. It's not that impressive. And what I want to do, there's some DNS requests, which we'll get to, which is full. And here's some TCP connections. We have ACKs, we have reassembled. This is WebEx. My guess is this might be, if I'm lucky at all, it's not going to show me the destination owner, which kind of sucks that it won't do that. But what I'll be able to do is look through here and see if I can find handshakes. So if I want to look and see, there's lots of reassembled packets. Here's a bunch of ACKs. Unseen segment. That's nice. Somebody acknowledged something I'd never sent. That's usually not a good idea. So tons of TCP. Here's some SYN-ACKs. So these are kinds of handshakes. You guys don't know that yet. But SYN-ACKs are signs of handshakes being done. This is one being done on our own campus. 151.101 might be the New York Times. One way to find out, you guys know how to tell? It's crazy, stupid, easy. Of course it is with Google. You can say just who owns 151, 101, 25, 164. And who is lookup domain? I know, isn't that like ridiculous? So hacker, that's okay. I'm just looking up domain name information. Fastly owns it. So Fastly is a New York Times web hosting server. I only know that because I've looked at their stuff a million times. So Fastly is somebody that will take content from your website and put it on a content distribution network so that it looks quickly for everyone else. One way to tell, to verify that, if you got this far and you can really tell what was going on, you could just try, I don't know if this will work, but I'm not going to take the time to do it the harder way. We can see if we can find 151.101.129. It's the same basic block, right? So that's a hint, right? So you can start picking up Scooby-Doo hints, like, you know, it's little clues that you know what's going on. Hey, I watched Scooby-Doo too. I watched it when it was new. Did you guys have Scooby-Doo when you were growing up? Was he still fun to watch? Did you guys like him? Okay, all right. So we loved him. I mean, he was like, I never missed that show. Of course, you knew you could never miss a show because there was no cable. There was no way to record anything. So if you weren't in front of the TV, you didn't get to see it. So our life was a lot more regimented, and I'm scarred to that. So okay, so back over to this. We can now go back, and we probably have answers to a bunch of these questions. So let's see if we do. Which connection type always produces the greatest HTTP delay? Non-persistent. And non-persistent will work. If you want to be more specific, can you tell me with or without parallel connections? Without. So non-persistent is accurate. That's a correct answer. But if you want to understand for yourself, it's ones without parallelism. All right, great. So let's plow on to the next one. Let me shrink my window here a little bit so we can have some space. I'm having space battles here. Which type of connection produces the least? And assume 4 objects and any per object transmission delay you want other than 0. Okay, we did all that. Which produces the least? Persistent with pipelining, right? So you remember with pipelining, this is the one where it looks like it's doing all 4 at once. You can't see it. That's why we drew it out for you guys. Okay, for the following questions, there are 4 objects being transmitted, and when we have the chance, we will choose 4 parallel connections. All right, which type of connection does this represent? One TCP, here, I get the HTML object, I receive the page, there's a little transmission delay, I immediately ask for the object, and it says there are 4 objects. So it looks like 1, but it says there are 4. So what type of connection am I using? Isn't it this one right here? It's exactly this, isn't it? So which one was I on? Persistent with pipelining. All right, makes sense? So this one's persistent with pipelining. All right, what about this one? Assume 4 objects. What's different? There's a second one. Right, so this is not persistent, correct? So it's not persistent, but at least it is parallel. So let's verify that. Non-persistent, but with parallel connections and 4 of them. Does that look like this? Yeah, okay, cool. Excellent. Which type of connection does this represent? I probably don't even need to go to the simulator. This is like the worst one of all, right? So it's persistent or not persistent? And any parallelism? No. So this might be from, a simple embedded system that's just grabbing objects one by one, doesn't need a lot of resources. This might be something that displays on a Best Buy panel at the airport where you can buy headphones. If you've gone to any really huge airports, they have these vending machines now that you can buy stuff. Okay. What type of connection does this represent for objects? Persistent or non-persistent? Okay, and how many parallel connections at once am I making? It's got 4 objects. Without pipeline, let's go look. So this one's a little more complicated. Without pipelining. So that looks right. So they call it pipelining instead of parallelism, but it's the same kind of concept, right? What do the persistent connections eliminate from the transmissions? What are they called? Handshakes. Yes. I think so, because when I turn off pipelining here, it doesn't do anything in parallel. If I turn pipelining back on, then it does 4, 3, 2, 1. It does everything in parallel. So they took away my ability to request how much parallelism. They just do everything they can once you get to pipelining. They just max out what the operating system and the browser will do. And in this simulator, it's at least 4. It's not going to be 4 in all systems. Some systems won't have the resources, but generally you should always have as many as you want. You can assume. I mean, you're not going to have 100, but you might have 10, for example. There's lots of battle over this, actually. There's lots of hacking that gets done, and when you try to limit the number of connections someone has, then they try to feed you parts of their web page from 2 different domains. So it's actually quite interesting, and it's from the website owner, not the browser. It's the owner that wants you to get the page fast. So if you're on a browser like Chrome, and you're trying to get 100 objects off of a page, like the New York Times, and they know that Chrome and the Apache web server here hard code in that no single user can get more than 12 TCP connections at a time, then you're going to have 7 or 8 round trips to get this done, 7 or 8 different connections, because you can't get 100 at once. You can only do 12. So what they will do is duplicate their domain at another site and another site, and these are completely different domain names. So this would be like NewYorkTimes.com, this would be NewYorkTimes1.com, and this would be NewYorkTimes2.com, and so forth. And these are different websites to your browser, and you can open up 12 connections to each of them. So as long as they feed you an HTML page that has 12 links here, go back to this one, and on that web page you look and there's 12 links that point over to here, and you have 12 links that point over to here, your browser will now go and get 36 objects at once instead of 12. And it's overwhelming the system, overwhelming the network, but it makes your page load really, really fast. So like, who cares? Why wouldn't you do this? It's called domain sharding. You have little shards, little pieces of your domain in various places. And it's bad behavior, but it's done. And so you have handshakes for sure with New York Times 1 and New York Times 2, but that handshake can go on in parallel with each other. You'll have your first handshake will happen here. Then you'll get the page back. You'll inspect the page. You will launch. This one will be kept alive. You will start getting 12 objects from here while you're doing a handshake with this one and this one. And you'll probably still be downloading a few objects when you begin downloading 12 from each of these. So it's a very effective way of pushing lots of web page at a user at one time. What's a little surprising is that it's the website owner that wants to do it, not just the website reader that wants to do it, the website provider. So you can pay a service to shard your domain and split it up over sites and edit your HTML page on the way out the door. They'll change some of the URLs to kind of balance it out. What most real sites do anyway is the stuff is not exactly sharded, but it's spread all over creation anyhow, because this is the New York Times, and this is doubleclick.net, and this one is Google Ad Services, and all those other URLs on the page, right? So these things are horribly complicated, and I think the Times has totally overkilled their web page. It's like a mess. It takes a minute to load now. Like, are you kidding? So I think they've gone too far. But they've done something in the last couple of years which they would have never, ever been able to do on printed paper. They've been able to grow their subscriptions by a couple of million subscribers because it's online. And they're shipping bits instead of atoms. And had they had to do this on print, they would not have been able to do it. If they could not have printed that many more papers with the press they had and distributed it and had enough trucks and paid all the postage, and it just would never have worked. So Trump hates their guts and calls them terrible names all the time. And every time he does, they get another 100,000 subscribers. So they're like, bring it, you know. So he's now sits down and meets with them. But it's fascinating. So this is one of the first times where we've seen the web enable the recovery of a failing business model. The papers were going under, and lots of them have gone out of business. And the New York Times is rocketing ahead. They're hiring people for the first time in years. They're hiring more reporters. They're growing their business. So they have figured it out. So who am I to complain and criticize their webpage? They know, obviously, better than anyone else in the industry what they're doing. So there's some hope for the real press, for the real media. If I ever see you watching a news YouTube video or FaceTime something where it's an automated voice that's reading the stuff, do not be surprised if I grab the phone out of your hand and we sit down and talk about where are you getting your news and why are you getting it there, because it's dangerous. You have to be really careful of where you grab your stuff, or you will become a tool. Okay, back over to, it's threatening the democracy in the U.S. actually. Okay, so they eliminate TCP handshakes. That's what you guys decided. If you compare persistent with pipelining to non-persistent with parallel connections, what part of the transmission cannot be eliminated from the non-persistent connection? So let's go look. Persistent connection with pipelining, you probably know the answer, right? Persistent connection with pipelining, okay, it looks like that. Okay, and the other one was non-persistent with parallelism. So what I'm going to do is take a snapshot of this and drag it over to the sketch tool, which changed my life when I discovered this thing. I was using WebExes before, and it was terrible. Okay, so here this is. So what can it not? Is that right? That's not correct. Why did it not copy? Why? It made the noise and everything. I heard it. There we go. All right, so what can it get rid of? Yeah, the second handshake. The extra handshakes. All right, good. Okay, switching gears, different problems. Keep going? This is helping? Okay, yeah, good. It's the way to do homework, I think. We just kind of go through it together. Plus, I think my observation has been you guys retain more of it this way because you're gaining confidence as you start seeing the pattern, and I'm here to answer any doubts as you have them. So this stuff will sink in. It lets me ask harder questions of you. I don't plan to necessarily do that. Okay, what is the unit of information called at each of these layers? Do you remember the units of information? This is like, is it a packet? So I'll give you a hint. None of them are packets. They all have different names. Do you remember what any of them are? Like at the data link layer. What technology exists at the data link layer? What is this? What kind of cable? Starts with an E. Ethernet. Yeah. So Ethernet is a data link technology. It's layer 2. The interesting thing about layer 2 is they usually bundle in layer 1 as well. So Ethernet not only gives you electrical requirements, but they also tell you exactly the cable you're supposed to use. So what do you call a packet of information on an Ethernet network? We can go look at Wireshark if you want. Here's Ethernet. What's it called? A frame. It's an Ethernet frame. So that's the unit of information. What's inside that frame? What's the most basic type of element of information that we know about in networking? The smallest piece of information. Bits. So the physical layer is concerned with sending bits. The data link layer is concerned with sending frames. What's above Ethernet? The network layer, where IP lives. Does anybody know what you call a packet of information in IP? It's not listed here. You want to Google for it? You want to take a peek? We can also go back and look at the book if we want, but unit of information in IP layer. Let's see, I misspelled it, but hopefully. So let's see what it says. PDU is not right, network packet, TCP5 layer. Let's take a peek at this. Oh, I just saw what I wanted on a different one. All right, so these are the layers. That's still not exactly helping me, but the next one is. I think this one will give me what I want. So let's go and peek at this one. All right, data encapsulation frames. So the Internet Protocol, that's not exactly true. That's not what our book teaches us. What they teach it, they have it down here, they call it more generically datagrams. And so what you'll generally find in textbooks is they will call packets at the IP layer datagrams. That's what our textbook calls them. Right? Packets is okay. Everyone calls everything packets all the time, universally. You'll never get criticized for it, but it's so generic that it's not very specific anymore. We're not really sure what layer you're talking about when you talk about packets. Okay, then here's the datagram, and this is, we're going to skip this because it's only going to confuse us now that it's wrong. So time to bail from this one and see if we can get to, here we go, Caroz-Ross. So let me find datagram here. Okay. Let's see if I can find it. Network layer datagram. Let me see what we have here. I want to find, all right, the transport layer deals in something called a segment. So there's a diagram in here, but this little table that you're building in the homework is going to be helpful to you. It's something you want to probably have on your little cheat sheet that you bring to the exam next week. So transport layer, we call these things segments. And how many does that leave? Where are we at? We just have one more to go, right? And it's the application. So the application is going to send a message. That's the generic word for the application. All right, so they walk through this in pieces, but it's in pieces. So that's why I gave it to you as a problem, just to try to get it all in one spot. If you read through here, you'll find that Caroz is very, very consistent. He does not mix the terms around. He's very careful to always call them the right things. So again, what we have are messages that come from the application. They are handed to TCP or UDP segments, and you hand them down to the network layer where they become datagrams. They're embedded into Ethernet frames and then transmitted as bits at the bottom. Okay, I drew something in red a few minutes ago and told you I needed to remember to come back and explain something important that was going on. So let me see if I can do that now. All right, one of the things I told you about was you got to figure out how TCP knows it's time to open a connection to someone. So when you start up your browser, if you don't have a default page, and I don't, I just have it open up to a blank window, but it doesn't automatically go to Google, for example. I don't have that set as my home page. Then there's no need for it to open a connection anywhere. I'm not trying to send data to anyone on the network. It turns out that TCP will not send a handshake until it has something from an application, the layer above. It will wait until you have something to send. So this is a little irritating because what this means is you show up at the restaurant and you're ready to sit down, and only when you show up do they clean off one of the tables. Like, shouldn't you do that when people leave instead of like, well, but how am I supposed to know which table you want to sit at? So that's kind of the idea. So there's a built-in delay for the application every single time there's a handshake. So that's another reason why we want to get rid of the handshake. Because the entire time TCP is negotiating this connection, your message is waiting. You've already made the function call, and you expect that the message has been sent. It just hasn't. It's not true. It hasn't been sent. Once the handshake is done, then finally TCP can take your message and send it over the network. Now it's able to actually build segments out of it. If the message is really big, then it may get broken up into different size segments depending on what the TCP software is capable of. Each segment goes down on its own, one by one, down to the IP layer, where it's put inside of a datagram. And it's possible the datagram is going to discover that the network that you're going to have to use, the physical link for this particular destination you're trying to reach, can't handle packets this big. So the IP layer may also divide up your datagram into pieces and fragment it further. And then each one of these things goes down to whatever the layer 2 protocol is, Ethernet. So your one message may turn into 100 frames on the network. It may go part of the way there and have to be further fragmented in the middle of the internet someplace when it has to go over a link that can't take even that size packet. So you can't count on at all how many packets are going to arrive at the other end. You have no way of knowing. You can ask that your packets never be fragmented, and if they get to a place where they need to, they'll just get dropped instead. But you can do that, and we'll learn more about that a little bit later in the semester. Okay, not all devices process all layers at the same time. You just saw that with this diagram. Close. There it is right there. So the hosts run applications. If you don't have an application, there's nothing to generate a message. If you don't generate a message, there's nothing to send on the network. It's that simple. So I send a message out. I know that my hosts all generate applications. Routers normally only run up to layer 3. And this diagram helps you remember that. Why? Well, they have to do Ethernet. That part's obvious. They have to physically connect to the network. And they have to know what frames are. So the wire and the Ethernet frame, okay, everything's going to have at least that if you want it to know what ones and zeros are. But on top of that, what's the next layer do? This is the IP layer. The IP layer handles routing. The IP layer looks at the address you're trying to reach and decides where to send you. The IP layer is the post office, and the router is the post office. So the routing software is the postal carrier. They look at the envelope, they look at the postal code, and they make a decision which truck it needs to go on next. They're making routing decisions. That's all they need to do. They do not know how to read whatever language you use to write the letter. They don't need to know how many pages of your letter are in this envelope and how many pages are in the next one. They don't need to understand what you're going to do if the envelope gets lost. They don't need to know any of that stuff. All they need to do is look at the address and make a decision. And if you let them just do that, it can be very, very efficient. So that's exactly how routers work. That's why they need that IP layer. So if I redraw this in ways that we've looked at in a couple of diagrams before, just to help you make a new layer here, I have a physical connection coming in. It is joined with a data link layer, so this would be like Ethernet. And it will leave in a minute out of another port, probably, out of another physical technology. Maybe this is wireless. It will still use Ethernet, but to kind of keep track of frames and things. So these are two different cables. They've shown up inside the same box. What's going to join these things together? Who's going to decide to pick this packet up, this frame, and drop it on this connection over here instead of another one back here in the distance that's got a connection that goes off in this direction? Who's going to decide to do it here and not here? The IP layer, the software running inside the system. It's the postal carrier. It looks at the packet as it comes in and makes that decision. So this is layer 1, layer 2, layer 3. This is also known as the network layer. This is known as the data link layer. This is known as the physical layer. This is datagrams, frames, bits. Okay. Switches, on the other hand, are simpler. I did not want to open it. Switches only need to go to layer 2. So switches are important because the assumption with the switch is there's really no decision making to make. And I don't know how much you guys know about the Postal Service, but I'm going to see if I can find a green relay mailbox. All right. So most mailboxes are blue in the United States, like this one. You guys have colors for yours as well, right? But some mailboxes are green. So these are switches in a computer network. This is what I would relate to a switch. This is called a relay box. This is where the post office comes and drops off the mail just to store it for a while until the postal carrier is empty-handed and needs to come back and pick up more. So here's a carrier that's got a little bicycle thing, and he can't carry all the mail for the whole neighborhood at once, so he just carries some. So there's no decision-making whatsoever to make. Nobody's going to look at the postal code and decide, you know, in which postal carrier's bag this needs to go through. There's only one carrier. This is his box. Everything in here belongs to him. So it just needs to be stored and then passed along. Any looking at the postal code was already done back at the post office. And the decision was already made to send it in this direction. So this is like an Ethernet switch on your LAN, because an Ethernet switch is just, you know, something that's going to look at the ones and zeros, build a new electrical version of the signal, and just send it on its way. It has a little bit of smarts. You know, it won't let you broadcast like crazy, and it'll cut off anybody that's got electrical interference. So it does some things to kind of maintain the health of the cable, but it's not making routing decisions. So it doesn't need IP, and that's good because this is hard to manage. This takes a specialist with certifications to do. Those people are very expensive, so we want them to manage as many devices as possible, and we do not want to put this software needlessly on lots of devices. It'll drive the cost of your network sky high. The administrative part of running a network is the most expensive part. It is not the $1 million switch. It is not the $100 million data center. It's not the $50,000 a month electric bill. It's the administrator. The sysadmins add up over time. They are the biggest improvement we've made in the last 20 years. The cost has dropped per server or sysadmin more than it's dropped any other way. More than CPU is sped up, more than storage has gone down, more than rent has improved, more than the electricity usage, more than the size of the server, physical footprint. The thing that we've improved in the industry by far more than everything else is the amount of system administrator time required to manage a device, manage a server or a router, because that's the most expensive piece over time. Those people are hard to find. So this device, we do not want to drop this software lots of places, as few places as possible. Okay, so a switch only goes to layer 2. Right, so that's what we see in this diagram. So it's just worried about, like, for example, getting it off of a Wi-Fi network and putting it onto Ethernet cable. That's what that device is doing right there. It only has one place to send every packet. It sends it to some router on campus. That's not the router. That's just the switch. Now, it does some routing in it because this is oftentimes the only thing people have, and so it has to do the routing. But in this environment, it doesn't have any routing to do. It's sending everything, every Wi-Fi frame it gets, it's converting from wireless to Ethernet, and that's it. So there's no looking at the postal code, there's no deciding, there's only one connection that leaves that, it only has one place to send it. So simple to manage, and works fine. All right, with that as your background, I want to make sure you guys remember that routers only run at layers 1, 2, and 3. We just talked about that. It makes its routing decisions at layer 3 and moves the packets along quickly. So far, so good. So most of the time, that's what routers do. This is why you don't ever see them, because all they're doing is routing. Do you have any idea who the person is that's looking at the postal code on your envelope inside the post office? Why would you care? Why would you know that? So you can do a trace route. You can have the envelope explode. I guarantee you'll find out who they are then. You'll meet a lot of people from the government if you do that. All right, so the router is sometimes not the router. Sometimes it's actually the destination. It's the router that you're actually trying to talk to. You're not asking him to pass something along. You're trying to ask that letter carrier, hey, do you want to go to lunch? You're trying to communicate with them. You send them a card that says happy birthday. It's actually for them. When that happens in a router, it's not just the router anymore. Now it's a host, just like your PC. What layer of software must it run? So what do you want him to do if you send him a would you like to go to lunch card? To send you back. What did you say? What was the word? Message. He needs to send you a message back, right? What layer are messages at? Application layer. So routers are also hosts. So this is confusing because most books will try to tell you that they only ever go up to layer 3. They don't. Every device goes all the way up to layer 5. It's just that most of the time we don't ever see it and we don't ever have access to it. Why do you want your routers to go to layer 5? Exactly. To manage them. So you can reach them, reboot them, change their programming, update the password, download a copy of new image software for them, change the routing protocol rules. All of that stuff used to require taking your laptop, walking across campus, taking a console cable, which was a little DB9 at one end and something at the other, and plugging into the back of the router and programming it. I've done that thousands of times. I hope I never have to again. It's not terrible, but it's extremely inefficient. Now it's all done remotely over the network. So even with switches, even with that little lowly layer 2 switch, it also has the ability to log in. You may need to turn it off or reboot it or activate another port or prohibit a certain MAC address from sending any more traffic on the network or see how many errors it's logging, etc. Or configure it when it first turns up. And it's tricky to design these things. When I used to build networks for franchise locations, we added it up once in my group, and I had over 1 million franchise locations in my customer base, which intimidated the hell out of us because we never had any idea it was that big. But we started adding them up. 22,000 McDonald's, 33,000 Shell oil stations, 16,000 Chevron stations. We had every oil company, so there was 250,000 there, easy. And we had insurance offices and Walmart stores and distribution centers and every kind of retail chain you'd ever heard of. We had Southwest Airlines with thousands of locations and Blockbuster Video, which had 8,000 still at the time. You know, all of these things all had some kind of a router at the site, but you hired contractors to do this. There are legions of companies with people that you ship them one of these kits. They put it in their truck. They'll go out to the store. The phone line has to be installed. It's an unbelievable coordination effort to get this done. And you have to design this router so that when you turn it on, how are you going to get to it? How are you going to connect to the router when it's the first time you've turned it on? So, yeah, so what you basically have to teach these things is how to phone home. So AT&T would build these devices, and they would have a public address that was reachable over the internet. That was the landing spot for all of these VPN devices. So the very first time the VPN discovered it was on the network, it would immediately open a connection to the mothership, is what we would call it. It would register where it was. It had some GPS ability. It would send us stats on the type of communication line. We would see the IP address it was using, and it would ask us, what do you want me to download? And that was our chance to download all the rules and the image that it needed. If you screwed this up and you didn't have it phone home, you could never reach the device. Excuse me, I don't know what's going on. Maybe it's time to take a break. In fact, it is. All right, so let's let's take a break while I choke to death. When we come back, I'm going to ask you the same question about not a switch, not a router, but a repeater, and then we have a few math problems to go through. So 15 minutes, sound okay to you guys? I'm almost over my goal, but obviously not completely, so I apologize. All right, I will pause this. It's 11:25. Let's come back at 11:40. All right, and we'll get this nailed out for you. All right, let me pull up the recorder. Sorry about this, guys. Repeaters are generally ignored by telecommunications textbooks that deal with networking, but they're really important in the fundamental distribution of signals. But they're dumb. They don't have any concept of ones and zeros. All they do is receive a signal and amplify it. That's it. So it allows it to continue on. So the telephone network for 150 years was built with lots and lots of beats on the network. So the problem is you amplify everything if you don't know ones and zeros, including the noise. So we usually filter off the high noise as well and amplify the signal. So these still exist. They still are present in all telecommunications networks. They're minimized somewhat because what we would really much rather do is put something intelligent that knows what ones and zeros look like, and then they can perfectly reproduce a brand new signal. So I'll show you what the difference looks like because it's very easy to see it when I draw it. So let's say this was your original signal, kind of nice and smooth, and it's subjected to noise, and the noise kind of looks like this. If you receive the red and amplify it, if it gets really weak over time, let me, hold on, I gotta mute something here real quick. Let's do that, share again. I heard it earlier, it was really soft. If it gets weaker, then it's gonna basically, you know, look a little more like that. So you can re-amplify it, but you're going to end up with something even uglier than what you have now. What you're certainly not going to have is this smooth curve in black in the background. So what a digital repeater will do is different. What a digital repeater will do is ask you the question, what was the pattern they were trying to send here? And even though there's noise, you can see there's kind of a peak, and then the red goes down here, and then it moves up. And the idea is that you're going to be able to, you know, repeat the signals that they were trying to send. And you're going to look down here, and you might conclude this is a -1, this is a 0. Whatever the values are, you'll be able to spot the original signal despite the noise. So if I drew it like this for you and told you if you received a signal that looked like this, could you still tell that it was that and not that? Yeah. You could easily spot that. So throw the noise away and rebuild a perfectly new signal and send that on down the line. So that's a digital repeater where it knows what ones and zeros are. This is why we do everything in digital and we don't try to do it in analog. But the technology is inherently analog. Electrons are analog generators. They're always going to be subjected to noise. Light will be subjected to interference. So this is what's really happening on every network on Earth. You just hope that you intercept it periodically before the noise gets bad enough that you can't tell anymore whether they were trying to send you this curve or this curve. Because if you get to that point, then you've lost the data. All right, so back to this question. I'm asking you about something that only takes the blue and turns it into the red. It knows nothing about ones and zeros. It's purely analog. Doesn't have any concept of frames or Ethernet or any of that. What layer is it running at? Just physical or data link? All it's doing is electrically amplifying if it's a... Yeah, that's all it is. There's tons of them out there, right? Tons and tons and tons. So very often people think like, well, if Ethernet always bundles the data link with the cable, is there really a physical layer out there anymore? Absolutely there is, and lots of devices that do it. All right. So for light, what you might do is receive the colors. Colors will drift, the wavelengths will shift, so you try to grab them while they're still pretty red, and then regenerate it with a new laser as pure red again. So this happens all the time in all systems. Moving to digital helped us tolerate lots more noise. Okay, so now let's go through a little bit of, we're going to switch gears a little bit. So I've got a formula for end-to-end delay. So if I have a packet of length L, and let me give us a new sheet here to start over, and I don't want to write in green. Hope that's not your favorite color. Okay, so you have L bits, and you've got a transmission rate, which is basically bits per second. And if you tell me how big the packet is, I'll tell you how long it's going to take to transmit onto this network. Not how long it's going to take to propagate across the network, but how long it's going to take to get all of those bits shoved on one end of the network. While you're doing that, the first bit is already racing off to the destination as fast as it can go. So by the time you finish, it may still be on the network. It may be already at the destination. Who knows? You're only worried about transmission. And if you tell me how many links there are on your network, then I know how many times it's going to have to go through this delay. So if I have a host and it goes to a router, I've got to transmit it onto the wire here, and then I've got to transmit it again onto the wire here. And once I make a routing decision about which way to go and I choose this one, I've got to transmit it onto the wire here. So just tell me how many links and you multiply it by this. All right, so that's the delay. So my question is, I've got 3 links, 2 routers, and 10 packets. And what I want us to figure out is the total transmission delay end to end. So how can we do it? There's a best practice for figuring this out. You can kind of determine your own best way, but there's one that I'll show you that's pretty foolproof. It's not totally intuitive at first, because what's confusing is part of this you're going to just track the very first packet, and then part of it you're going to look at all the rest. And the equations are not the same for the first packet and for all the rest. That's what makes it a little confusing. So let's start with the first packet. I have, at time 1 times the delay, the packet has dropped onto the wire and it's moved to the first device. And there's 9 packets behind me. So I'm only looking at the first one. At time 2 times L over R, I've advanced 1 position, and I'm still pulling all these behind me, but I'm ignoring them for the minute. I'm just following the first packet. So I've transmitted it once to get it here. I transmitted it once to get it here. I transmitted a 3rd time and get it over here. Only then does the packet arrive at host B. So 1 packet, mission accomplished. 3 times L over R, and I got it there. And in this problem, apparently we're supposed to assume there's 0 propagation delay and there's no delay in the router. So we're only looking at transmission delay on this problem. Okay, well that makes it simpler. I guess it also makes it a little confusing, but okay, that's fine. What about the remaining 9 packets? Where is the second packet? When I transmit here and it instantly arrives at the host, where's the second packet? Well, if there's no queuing delay in the routers and there's no propagation delay, it's ready to transmit on this link at the same time I'm ready to transmit on this link. And the third packet is over here. He's waiting to transmit here. The second one's waiting to transmit here. And the first one's waiting to transmit here. So they're just 1 transmission delay behind me. Because if I let things go forward 1, then 1 is finished, 2 is here, 3 is here, and 4 is here. So I've already counted how long it takes to drag the first packet all the way over. Every other packet will show up, L over R behind me, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then they will all be here as well with me. That's the idea. So for the 2nd through 9th packets, the delay is only 1 L over R, not 3. or I'll double count it. So there's 9 of these packets left. So that's basically the total amount of time, but we're going to write it as an equation. So let me get it here. The first packet takes n number of links times L over R. So that's what the first one is. And the rest of them require P minus 1 packets, if that's how many there are, times L over R. It has nothing to do with how many links there are, only with how many more packets are left. So this is the first packet. This is, if there's total of P packets, P minus 1 left over here. Believe it or not, that's your equation. So n minus 1 plus P over times L if you want, however you want to write it, but it's basically these two elements up here. That's probably the easiest way to throw it up there. All right, the building block is L over R. That's the transmission time. So this is good if every one of these things has the same transmission rate. They don't always. Different links sometimes have 100 megabits, the next one has a gigabit, and one of them has 10 megabits. So they're not always going to be the same. So what if we add propagation delay to each link? How are we going to change the equation? We're still going to have all the same transmission delay, right? What are we going to do for propagation delay? How many propagation delays are there on this network? What is propagation delay? It's on the link, yeah. So how do species propagate? What does it mean for human beings to propagate? To multiply, right? Takes 9 months, doesn't it? Okay, propagation delay must be delay. How long it takes to get there. You can remember that, can you? Propagating humans, propagating networks. It's easy enough. So there's like 4 different types of delay. We got to have some kind of trick to remember some of these things. Anything to help. So propagation delay is how long it takes to get to the other end of this cable. So how many links do I have on this network? So I'm going to have 3 times propagation delay. So if I generalize that, where was the number of links up here in this equation? Does anybody remember what it was? P is the number of packets, right? Is N, what was N? So that was the first packet. And the first packet had how many? This is transmission delay here, right? So what was N? What was the value of N on this network? How many times did it get transmitted? 1, 2, 3. So N also looks like it's the number of links. Maybe we could use N to do that. So we've got N of these, P minus 1 of these, and now what we're saying is we have N times D prop as well. That will work. We can crank it out that way if we want. The other way to go about this is to say at every host I have a transmission delay for the first link, and for all the rest of the links I have both transmission delay and processing delay, or propagation delay rather, on there. Is that right, or is it on all of them? No, it's on all of them. It's on all of them. I'm leaving one out. So for every one of these links, I'm going to have to transmit it, and I'm going to have to propagate it. Right? That's what I'm going to have. I'm going to have transmission delay, and I'm going to have propagation delay. I know I'm going to have it N times for the first packet, because this guy was the first one, and I'm going to have it this many times for the remaining packets. Are these packets going to have to propagate across the network also? Yeah, just like the first one did. So when I add propagation to this, I need to also add it to this. So I have N times over here, I have P minus 1 times over here, times what? Times L over R plus D prop. So this L over R plus D prop is going to be applied to the first packet, which goes through in links, and then however many are left packets, it's going to be the same thing for them as well, L over R plus D prop for them. So if I write this a little more neatly, maybe I can clean this up a little bit. A different way to write this might be to say it's going to be N plus P minus 1 times what? Transmission delay plus propagation delay. Does that look neater? So the first packet has N links to go over. At each link, it's going to get transmitted and propagated. Second link, transmitted, propagated. Third link, transmitted, propagated. Now it's made it to the other end. The other packets are streaming behind it. They're not waiting over here. They're right behind me. So if I allow one more transmit and propagation, the second packet will arrive. And then the third one will arrive with just one more after that. And the fourth one will arrive immediately after 3. So for the rest of them, it's one less than the number of packets that I had. All right, make sense? Do you think you could reconstruct this? If you just visualize every place where it needs to be transmitted, and remember propagation takes 9 months. It takes time. Usually the longest part of your network delay is the propagation delay. The routers are not your problem. Usually the problem is you have a 4,000-mile undersea cable to go over. It's going to take 100 milliseconds. That's usually your problem. So propagation delay typically dominates network delay. This is another reason why people want to put copies of websites close to you so they can reduce that. Okay, so far so good. Car caravan analogy. Do you guys remember the car caravan with the toll booths and the vehicles? We went over that. Okay, suppose the caravan travels at 300 kilometers per, at 100 kilometers per hour. So it's going to take 3 hours to get there. And we begin counting just as the group decides which booth they'll use, that should say use, and the first car pulls up to the booth to begin payment. So the gate's not open yet. We've all pulled up as a row. Everybody's going to get in the same line. We're at the autopista, ready to go to the airport, and we need 15 seconds for the person to process our payment. First car shows up. First car waits 15 seconds. The gate opens. They take off. They start driving towards the next toll booth. And they're evenly spaced. They begin at toll booth 1. They pass through toll booth 2 down the road. They're going to have to stop again and pay. It'll be another 15 seconds. After 15 seconds, the gate will open at toll booth 2, and vehicle 1 will continue on its journey. It will make it to toll booth 3. It will stop and pay a toll. Wait 15 seconds. The gate will go up. It will leave toll booth 3. It will drive 30 more seconds, and then the race is over. So we can draw this. Toll booth 1, toll booth 2, toll booth 3, and then 30 seconds more. So I don't know how long that is. We could figure it out, but they told us it's 30 seconds. So there's 15 seconds here, 15 seconds here, 15 seconds here. There's a total of 300 kilometers. So there must be 150 kilometers here and 150 kilometers here. If I'm going at 100 kilometers per hour, how long is it going to take to go 150 kilometers? I can do an hour, 100 in an hour. How long is it going to do 150? Exactly. 90 minutes. And we'll make it 90 minutes here as well. Everything else is seconds. See how propagation delay takes most of your time? It's really bad in this example. But this is reasonable. You could imagine being on a toll road. You're willing to wait 15 seconds for the toll booth. That's not bad at all. And then drive for an hour and a half. That's like driving from here to Laredo. You know, that's about the way it works. Okay, how long will it take a car to propagate from one booth to the next? You just answered that. You just told me what that was. Okay, so that's A. What is the end-to-end delay from the time the first car pulls up to toll booth number 1 to the time the last car passes toll booth 3 and finishes that last 30-second stretch. Ooh. Good thing we did the other problem first, because we're going to need what we learned. Which vehicle should we try and track first? You like that methodology? Is that okay? Let's look at the first car. Let's figure out how long it takes to always go through. And then we'll figure out how far the second car is behind us. And we'll just do it that way. All right, so what's the delay for the first car? I've got some toll booth delay. That's 15 seconds. Times how many times? All right, and then I've got propagation delay. I've got 90 minutes, you said. Looks like we have a couple of those. And plus 30 seconds. This weird last finish line thing over here. You don't want to finish at paying at the toll booth. That's no fun. You know, you hand the money and go, yeah, you know, people aren't that excited. Is there anything else? Is that it? We're looking at the first one now. There's a total of 10. Did I ever tell you that? I never told you how many cars. How amazing is that? And I also left out another. Yeah, so let me change that. Has 10 people. And you're happy now? Yeah, that would be vaguely important. So thank you for catching that. So let's add it up. 180 minutes here. I have 15, I have 45 seconds here, and another 30 seconds here. So that's 1 minute, 15 seconds. So what is that, 181 minutes, 15 seconds? Does that sound right? All right, so let me see what else I wanted to cover on this in my notes. Okay, did I figure that out? Is that true? So that's it for the first one. What about the other 9 cars? How far is the second car behind me? 1 toll booth behind me. But is he going to wait until I get to toll booth 3 before he leaves toll booth 2? So let's go all the way back to the beginning. I wait 15 seconds. I start driving. How long before he pulls out of the toll booth? 15 seconds. He's going to be right behind me. So the second car is 15 seconds behind me all the way through. At the second toll booth, what happens? I pull up. I wait 15 seconds. I leave. He's pulling up. He waits how long? 15 seconds. So it's he's 15 seconds behind me. So if I don't want him to wait in line at the toll booth, I had better be out of there before he arrives, or at least as he arrives. Did I? He's 15 seconds behind me. In 15 seconds, he shows up. Where am I? Gone. I just left. So this works. There's no delay in the router. So the remaining 9 cars, it's not as bad as you thought. Right? The second equation is simpler. Right? So this is why it's not intuitive. I'm like him. I saw what he did and went, ugh. Like, that's what I do. When I see the second car, I think it's going to be the whole thing again and again and again. So that's what makes it not intuitive. Right? So he's got the right intuition, which is this doesn't exactly make sense at first. All right, so 9 cars, that's how I feel about it. 9 cars times 15 seconds is going to be 2 more minutes and another 15 seconds. Right? So we're looking at 183 minutes and 30 seconds. Because it was 45 seconds to the 3 toll booths, plus 30 seconds at the end after you finish the toll booth. There's a last 30 seconds. That gives you 1:15. On top of the 300 kilometers you drove, which took 180 minutes. Just down to 121 in 15 seconds. It's a weird number. Doesn't come out nice and even, unfortunately. So 183.30. You guys believe that? So this is one that's not necessarily the easiest in the world to do, but hopefully if I did the math right, that's the answer you'll get also. All right? Anybody disagree with that? I do make mistakes, so it's possible. All right, consider two hosts A and B connected by a single link of rate r bits per second. Suppose the hosts are separated by m meters, and suppose the propagation speed along the link is s meters per second. Host A is to send a packet of size L bits to host B. Oh my gosh. All right, express the propagation delay in terms of M and S. Okay, so we're going to do this piece by piece. So the propagation delay is what unit? What kind of measurement is propagation delay? It's in milliseconds, it's time. So milliseconds will be fine, or for now, let's just say seconds. All right, so I've got seconds, so that's what I know I need to get up. And I have meters and seconds, so how am I going to figure this out? The delay in propagation time. Do I have something that's got meters? Yes, I know how far apart the hosts are. And what else do I have? I have something that's meters per second. So if I divide that by meters per second, I'll be done. So that's it. Right, so my d prop is equal to meters divided by propagation speed, which was s. And did I have a name for the distance? No, it's just m. Probably should have been d or something like that. But okay, that's okay. And the answer will be in seconds. That one's a lot easier than it looked. So I was teaching somebody the best comeback for, hey, you're smarter than you look. You guys have a response to that? It's better than looking smarter than you are. So I had a boss once that said that to someone. All right, determine the transmission time of the packet. Now we're going to look at transmission time. All right. And obtain, let's see, in terms of L and R. So transmission is also going to be seconds. We're looking for time again. And what I have is bits, and I have bits per second, because this is the size in bits, and this is the transmission speed in bits per second. So what if I divide it? That'll cancel out the bits and put seconds back on top. That'll give me what I want. Agreed? So what's that formula? D sub trans equals, we just talked about this one, L over R, right, in seconds. Right, so little building blocks. These are good ones to have around, these little equations. Suppose A begins to transmit the packet at time 0. At time D trans, where is the last bit of the packet? So what they're asking is it still on the network, or is it at host B? How are we going to figure that out? We know what D trans is. We just figured that out, right? We didn't really do numbers, but we have the formula. So we know. Oh, no, we skipped it, didn't we? We need it. So let's do it. Ignoring processing and queuing delays, obtain an expression for the end-to-end delay. Well, it's D trans plus D prop. Just add the two together. So you could also just say M over S plus L over R. Okay, so that's how long it's going to take to actually transmit and get to the other end. So what this one is asking us on D is, where's the packet? Oh, this one's asking something simpler. This one's actually much easier. This is asking where the last bit of the packet is. So after D trans, where is the last bit of the packet? Not the first, but the last. Just like the last car in the toll booth, it's just entering the network. It's just being transmitted. So at D sub trans, it's just entering the network, just leaving host A. Okay, so let's look at some actual greater than, less than questions now. Suppose the time it takes for a bit to get across the wire is greater than the time it takes to transmit the entire packet onto the wire. So it takes longer for a bit to get across the wire than it takes for me to transmit the whole packet onto the wire. If that's true, then after this amount of time, where is the first bit of the packet? Is it on the network or at the destination host? So what they're telling us is D-trans, they're telling us a relationship that D-prop is less than D-trans. Is it? All right, so let's start off at time 0. The first bit is here, and the last bit is here. Yes. I'm doing, okay, so the next one does it exactly the opposite. So we're going to do it both ways. All right, so we'll do it both ways. Thanks. D-prop is greater than D-trans. So we'll get both answers in here. First and last. So it transmits on the wire. The clock starts ticking now. At D-trans, let's say it's here. My first bit is here. And the last bit is just entering the wire. Correct? This is all drained out. It's all on the network. So my packet looks like this. So what's the relationship between D-prop? If D-prop is greater than D-trans, then D-prop is somewhere over here. Correct? It's bigger. If D-prop is less than D-trans, D-prop is over here somewhere. In which case, this is inside the host. No more network. If D-prop equals D-trans, then it's exactly right here. So I can do without drawing them out, or at least it helps me a lot. So I just draw it. I've drained my packet out at time D-trans. If the cable was infinitely long, it had plenty of room, it would be here. And the last bit would just be leaving. So D-prop greater is over here. So the first bit is still on the network. Is that what we decided? When it's bigger. If D-prop is less, if D-prop is less than D-trans, then I will have reached the end of my propagation time before I finished my transmission time. So that meant that bits started already arriving and coming up into the host before I finished draining my packet completely out onto the network over here. Make sense? So there's 3 possibilities. You're either going to have a network that's exactly the right length to get completely filled with one packet perfectly, or it'll be too short or too long. It does happen. And in fact, there's a measurement for it. It's called the bandwidth delay product. So you can figure out how many bits you have in flight at risk on a network by calculating that. And there's sometimes the network is so long, you might never want to do that, because if something goes wrong, you've used up tons and tons of time. But it is a measurement. It usually happens on WANs, not on WANs. On WANs, there's so many users that need to share the network that you want the transmission rate to be really, really high, so you can get lots of packets on right after each other while they can all make their journey together across the network. So we saw this in the simulator that you guys used. There are samples of when you are still transmitting a packet and the end of it has already arrived. Right? And there's sometimes when it hasn't. Okay, so when D-prop is greater, it takes longer to get across the network than to transmit. So your first bit is still going to be on the network at D-trans. If it's shorter than that, you will have run out of network before you finish transmitting. And so some of the packet is going to have to be in the host. You don't have enough network to hold the whole packet. Okay, after how much time will the first bit be delivered to the waiting application on host B? Well, didn't you answer that before? Isn't that exactly the same thing as transmission time plus propagation delay, or is it something different than that? So this is a little bit of a different question. Think about the way a network actually works. A packet starts to arrive at your router. Do you want to start handing the bits to the application yet? Why? Well, why doesn't it make sense? Yeah, but I send you television signals as they show up. I don't packetize any of that. The answer is right, you don't. Why? Why do you wait? What are you worried about? Is the network reliable or unreliable? Can things happen to your packets? Can they get lost? Can they get rerouted? Can they get duplicated? Can they be interfered with, corrupted, collided? All that stuff happens, right? So what do we do to a packet to check to make sure? When you download a file from Microsoft before you install it, how do you make sure the file came over correctly? Do you guys ever pay attention to that? Like if I go to NS3 to download network simulation package, which is open source, and I go to the website, free download, and I look at download for Linux, and let's see here, do I get the, they're going to show me, usually on these, I'm looking for a long string of numbers. Why? Why am I looking for a long string of numbers? You guys ever notice that when you download stuff? Like when you download from Microsoft.com? So here's the asset. I'll go ahead and download it and see what happens. I don't want that one. I'm going to write a letter to those guys today. I don't want that one. No, I did want that one. Where did it? Here it is. I'll pull it up. Okay, verifying. What does this mean here? What does it mean verifying? It says verificando. How is it verifying package? What would you guys do? Do you just trust files that get downloaded? Maybe. I kind of do usually. I don't usually go through the step. But there are checksums that they give you. And what they basically want you to do is once you get the file, you run it through a little simple algorithm to create a remainder. And you check to see if the remainder, when you calculated it with what you downloaded, is the same remainder that they publish it should have. And if they match, then you know the file probably hasn't been corrupted at all. It's mathematically, theoretically possible, but extraordinarily rare that you could change the bit patterns and come up with the same remainder. Unlikely. So there are checksums, and they're on packets too. We will wait until an Ethernet frame arrives. We will divide it by, run it through a little math formula, and see if the remainder matches what's at the end of the frame. If either that number got corrupted or the frame got corrupted, then they should not match each other. We should not be able to recalculate that number from what we got, and we have to throw the frame away. So routers do this for every packet. They do basic checking to make sure it hasn't been corrupted. That's important. So that's one of the ways they overcome from the fact that it's error prone. They add some error correction into what they're doing. Okay, let me see which file it was. I think it's this one. Okay, so after how much time will the first bit be delivered to the waiting application? The real answer is only after the entire packet has arrived. because you can't check if it's all there correctly until the whole thing arrives. So this is not a math problem. That one turns out to totally be a policy question. So when do all of them arrive? That one is what you calculated before, transmission plus propagation. That's how long it takes to get the packet there. Remember, every link you transmit and propagate, transmit and propagate, transmit and propagate, every packet. Okay, let's put some real numbers in. Suppose the speed is 2.5 times 10 to the 8 meters per second, 200-bit long packet, 56,000 bits per second for transmission speed. Find the distance so that dprop equals dtrans. So what is dtrans? Let's calculate that first. How long is it going to take to transmit this packet? What's the formula for dtrans? Look back up above if you have to. L over R, which in this case is 200 bits divided by 56 E3 bits per second. What does that equal? So we can calculate it. 200 divided by 56,000. That's that weird number. Did you guys get that too? All right, I'm going to multiply by 1,000 to get milliseconds. So it's roughly equal to so I'm just going to keep it for a minute, 3.5714. That's not a number I need. That's not the question I've been asked. This is an intermediate value. So maybe I should continue on and figure out, now that I have this number, this is how long I have. So now I need to figure out, since I want dprop to match this time, and I know how many meters a second I go, if I go that number of meters per second for this long, it'll tell me how much I traveled. Does that make sense? So this is milliseconds. So if you take a network and you travel for this long at a speed of 2.5 times 10 to the 8 meters per second, should I divide or multiply S? If I divide, I'm going to get seconds over meters per second, and that'll give me seconds squared over meter, right? What if I try, let's try multiplying. What do I get then? Times meters per second. Okay, this one looks better. All right, so I want to multiply L over R by S. And S is 2.5 times 10 to the 8th. So let me go back to this horrible number and multiply it by 2.5 E8. Of course, I blasted out the other one, so I screwed that up. 200 divided by 56,000 times 2.5 E8. And 200 bits. Is that right? Yeah, but why am I getting a much larger number than that? Thank you. That's why. I asked for kilometers. So it's 893 kilometers. Can you believe that? That's like amazing. And the time it takes to transmit one packet, you can go 900 kilometers. Really? Really? If you wanted to go less distance with that packet, what would you do? If you didn't want it to require 893 kilometers, if you wanted that number to be less, what would you change about this network? Which rate? You could increase the transmission rate. It would take a lot less time to get it on the wire. Could you make the packet size different? Smaller? Can you change the propagation speed? Yeah, probably not. I may give you a problem with just some weird propagation speed just to do the math with a different number. But the reality is we're pretty much stuck with this propagation speed. We usually can't do anything about it. We're stuck with 2.5 times 10 to the 8th. The book uses 2 a lot. That's okay. I mean, pretty soon, 900 kilometers, 850 kilometers, I don't want to run either one in a race. Okay, next one. So 893, is that what we agreed on? Thanks for keeping me on the right problem. Consider a packet. Now we've got a bunch of links here, 3 links, L-1 routers, L links. So I've kind of mixed and matched how many I'm telling you here. So what I want to do is first come up with just the equation, and then we're going to get to the specific numbers. So this really should say L links for now, but I'll walk us through this together. That's not a big problem. So I've got a packet of length L. It's going from A to B. It's going to travel over L links. So I know that I'm going to have L-1 routers, because you always have one less router. And I have the length of each segment, the propagation speed of each segment, and the transmission rate of each segment for, in this case, three links. I'm going to add processing delay and queuing delay at each router. So what's the total end-to-end delay for the packet? Wow. Okay. Here's the way to go about this without losing your mind. This is a summation. From I equals 1, first to some of my things is going to depend on the number of routers I've got. And some of the things I have, it's going to depend on the number of links that I've got. Correct? Like processing and queuing delay only happens in the routers. And transmission and propagation delay only happens on the links. And there's not the same number of those two things. So let's use 2 different sums. This one's going to be the number of links. And this one, L-1, is the number of links minus 1, which is the number of routers. Make sense? Okay. Which things go into each router? What delay did they tell us happens inside of each router? These here, right? All right, and do we know whether it says they're constant? It doesn't say they're different for each router. So I'm going to say dproc plus dq. Nope, I did it on the wrong side. Yep, thank you. Deprocessing plus dqing. Okay, we're done with the routers. That's the formula for the entire contribution delay that the routers will contribute to any network. If you tell me how many there are and how much delay is in each one of them, I'll just add them up like this. All right? I did it as a sum instead of multiplication because it seems to be a little more sane to me. Okay, what about the links? What happens on every link? Yep, T-trans. I'm going to write them backwards. And propagation delay. But are they the same on every link? They told us they have different values for each one. So here's where the sub I comes in. So if I add those together for each link, then I'm finished with the links. That's it. That's the answer. There's no simplifying it beyond that. It's just that easy. We could go crazy and try to turn it into M's and D's and R's, but I'm not. This is good enough. I just want to make sure you understand there's some things that the routers contribute, and there's some things that the links contribute, and they're not the same thing. There's one less for the routers. You'll notice not here anything having to do with the hosts, how much buffer they have, or any of that stuff. Okay, let's plug in some real numbers now. You will see this diagram on the exam. I can tell you that now. So this used to be 15 different questions, and I threw it all in the trash over the weekend and said, this is ridiculous, let's build a table and just fill in some blanks. Well, it's just insane. It's crazy. So I put some stuff in. The way this thing is organized is a little bit interesting. What you have are, let's see, is it going to copy it for me? It may not. No, I'm going to have to take a picture of it. That's okay. Let me do this first. There we go. I've alternated the rows. Right, you see I've alternated them? There's a row for a link, and then a row for a router, and then a row for a link, and a row for a router. So there's one more link than there is router. That's exactly what we have. That's reality. So you could draw this network. You have A here, you have router 1, router 2, and you have B here. So these are the routers. And there's link 1, link 2, and link 3. So that's what I've got here. 3 links, 2 routers. The transmission rate is 2 megabits per second. I have to be careful with the units. This table says give it to me in kilobits per second. So I had to multiply it by 1,000 to turn megabits per second into kilobits per second. So I've been given that. I know the processing and the queuing delay. I was told it's 1 and 2 here, so I didn't have to read it. I've already put it in the table for you. I have the cable length. They're different for each link, and the propagation speed's the same for each link. So let's start filling in the blanks. What is my transmissions delay here? So somebody do it and tell me what it is in milliseconds. I have 1,500 bytes. No, they're not. Bytes is 8 bits. So if you're given bytes, always multiply by 8 to get the number of bits. Good catch. So this is 12,000 bits. And your transmission rate is 2 million bits per second. So it's 12,000 divided by 2e6. Milliseconds multiplied by 1,000. 6. So I will tell you from experience, if you have a 1,500 byte datagram to transmit over a network that's 2 megabits per second, 6 milliseconds sounds reasonable. I wouldn't expect it to be seconds or microseconds. It's going to take some milliseconds. So each one of these is the same, right? Because the speed's the same for each of these. Now it's on the network. The router delay is already given to me in milliseconds for processing and queuing. That's trivial. I just add those together. 3 milliseconds per router. Just have to put it on the correct row. Then I have cable length and propagation speed. So somebody do this one for me. Remember this in kilometers, and propagation speed is in meters per second. So how long is it going to take for a signal to travel across the 5,000 kilometer cable? This column? This one? Over here? Left or right? I can't tell where you're pointing. Left to the right? This one here? This is the router, total router delay. Overall router delay. So I used RTR for router. I didn't have room. So we don't really have a measurement for this. I just wanted a subtotal so we don't have to add 10 things together. I want to make it simple at the end. So here's the delay. So if I have a 5,000 kilometer cable and I can go 2.5 times 10 to the 8th meters per second, how long is it going to take to go across that cable? How do you do it? You divide. So what's the answer? Somebody do the math for me. And convert it to, remember you convert the kilometers to meters. So take that value and you're going to multiply by another 1,000 to get into the meters, and then you divide it by your propagation speed. And it'll give you an answer, but I would like it in milliseconds, if that's okay. Anybody else get something? Let me try it. All right, 5,000 meters times 1,000 meters per kilometer divided by 2.5 E8. That's seconds, multiplied by 1,000 milliseconds per second, and I get 20. So the first one takes 20. What does the next one take? That makes sense. 20% less, 16. And what does the last one take? It's 1/4 of 4,000, so it takes 1/4 as much time. So what is transmission plus propagation for the first link? And what about for the second one? Very good. And the last one? 10. So the total delay for the first link, here's how I would do it. I would say 26 for the first one because we haven't gone across a router yet. By the time we get to the second link, we had to go through this router. It adds 3, bringing my total at the end of the second link to 25. By the time I finish going through the third link, I will have gone through the second router to get there. It also adds 3 milliseconds of delay, increasing my 10 milliseconds by 3 for a total of 13. And the grand total is 64 milliseconds. So for the first one, there's no router. It goes straight from the computer onto the link. So this is the total delay for the first link. Now I'm done with the first link. What's next to go through? I have a router and another link. The router takes 3. That link took 22. By the time I'm done with the second link, it's a total of 25 for that router and link. Now what do I still have in front of me? I have one more router and one more link. They took 13 to go through. Does that make sense? Okay. Can you fill one of these out? If I give you different squares to empty to calculate, could you do it? If I ask you to tell me what's the propagation speed of each link, and I give you the answers, or if I tell you what's the transmission rate. In fact, what I would like to do is to do something like this. I would like to leave this blank, this blank, this blank, and maybe this blank, something like that, and give you everything else and have you figure it out. So how would you go about figuring out this? Well, you can just do the subtraction. If this is 20 and this is 6, and you know I'm telling you it took 6, I have to tell you how big the packet is, you can figure out how fast must this thing transmit to get 12,000 bits done in 6 milliseconds. So you would do bits divided by seconds, bits per second. You would come up with 2 million bits per second, right? So I'll try to give you one that does just this. I'll do it myself. If you want to practice this, I can give you guys the spreadsheet that I built that calculates all this stuff, and you can play around with it and just try drilling yourself. You'll have to change the formulas around because what mine does right now is only the ones that you see. I have to type in the 2,000 and I have to type in the 4,000 kilometers, but you can change it around and mess with it. It's not hard to build your own if you want to do that. The real important thing is you're going to need the formulas. You're going to need to walk into the exam and know how to calculate transmission rate given packet size and transmission time. You're going to have to know how to do that. So you want to write that formula down. So, and you're going to need to know like what it means in Spanish, not just as a math formula. You're going to know when you see L over R, that's how long it takes to transmit the packet. It's got to mean that to you. So just write those things down or copy the formulas from that previous problem in this homework. Just copy them down and bring them with you. All right, we have a little bit left and we're almost out of time, but let's see what we've got here. This one is not, this one's a little different. So, did we finish? Yes. I just added up the processing delay and the queuing delay. Those are the two types of delay that the router contributed to my misery. So it doesn't have a variable name. I just wanted a subtotal so it would be easier to add things together. So I may give you something a little harder than that on the test, but that's all that is, total router delay. And those two things are the only things that happen in the router. How long it takes to figure out where to send it, and then to actually get it into the queue. Okay, suppose the transmission rates were all the same, and the queuing and processing delay was all 0, and it does not store and forward packets. Oh, this is a really big change. What I'm telling you is as each bit arrives, I already have made up my mind ahead of time where it needs to go. There's no looking up. There's no time to look up. Processing delay is 0. There's no time to get it into a queue. There's no delay because there's no queuing time. It's 0. I told you it's 0. So this is the way the phone network works. Any deciding which path you're going to take, you do at the beginning of the call. You type in the telephone number. When you hear the ring, it's telling you they figured out the path end to end. Every device from one end of the world to the other has already reserved the bandwidth, and it's made the connection, and now it's trying to get the person at the other end to answer. So from that point on, when you start pouring bits into the telephone, they're going to go bit by bit to the other end. So if that's the case, does it change the end-to-end delay? Will the bits of a phone call arrive at the destination sooner than if I had put them on a data network? What does your intuition tell you? Have you ever listened to a live radio station or watched a live television station over cable at the same time you're streaming it on your phone? Which one's sooner? Yeah, the broadcast one's always sooner. Broadcast is not store and forward. Networks are. Data networks are. So it will happen sooner. The situation on this one is it's basically just one transmission delay, and you just add up 9,000 miles or 10,000 miles of propagation, and that's it. Right? So that one's super simple. So I got it to be 6 milliseconds for the first transmission delay, and then 30, 40 for the propagation, so a total of 46, as opposed to 64. So that's, different. I have to get the bits onto the wire. It's still a packet, so I have to get all of them on there, and then each one of those bits is going to have a journey of 5,000 plus 4,000 plus 1,000. There's 0 along the way in the routers. So it's just like it's one cable of 10,000 kilometers long. How long does it take to go across 10,000 kilometers? 20 plus 16 plus 4. I already calculated it. It's propagation delay. So this is 40 and 6 to get them on there. So the answer, 46. Well, it's the first 6. It's the ones to actually get the packet onto the wire to begin with. So what I'm basically asking is the end-to-end delay of your packet, not of just the bit. The propagation delay of any bit is just 40. That's it. But because you've got 1,500 bytes you need to send, how long before you get those 1,500 bytes at the other end? 46 milliseconds is the answer. This is why people still build circuit switch networks. They're faster. If you're a stock trader, this is what you want. You want to get your trade done 20 milliseconds before you'll be a billionaire in no time. I mean, it's like a life-changing difference. We used to build routers that did crazy stuff. If we have time, I'll tell you guys about it. All right, number 9, Little's formula basically says, and it tells you what it is here. If I have a certain number of packets arriving and you normally find so many in front of you in line, this is like the post office, plus somebody's halfway through buying stamps, what's your average packet arrival rate? So this one's a little harder. I don't know that we'll have time to go through the whole thing, so I'll give you guys the solution for it on Friday. I would like for you to try to do the calculation. I'll give you kind of a sneak peek at it. The way you're going to do the calculation is, you know, N equals A times B, and you can watch this on the video. You don't have to write all this down now. So you always have, we have 10 packets, but there's always one currently being transmitted. So you always add 1 to the number of packets that are in the buffer, because one of them is at the front being transmitted right now. So there's 11 of those. That's what N is, and that's going to be equal to A times DQ plus D trans. So we have 11 packets equal to A packets per second times, and our queuing delay was 0.01. They told us that. They told us it was 100 packets a second, so each packet arrives 1/100th of a second apart. Because they said if there's 100 of them a second, then each one is 1/100th of that. That makes sense. So that's equal to A times 0.02, because that's what this adds up to, is just 0.02. So A then is equal to 11 divided by 0.02. A is equal to 550 packets per second. That's how you do that problem. So add 1, and if they tell you how many packets a second, flip it, and that's how many seconds per packet. Duh. That makes sense. I think that's the way it works. It's just upside down. Okay? If you got solutions from this from a previous semester or something, it was wrong. I copied out of the book, it was wrong. The solution I'll give you is correct. I just read it all over myself, because that's my curse. I can't trust the publisher's textbook. Let's see, there's also one. Okay, so this is really simple. This one's easier than the last one. There's a buffer that holds 2 packets, plus there's 1 packet that's 50% transmitted. So there's actually 2.5 packets in front of me in line. Each packet is 1,250 bytes times 8 bits per byte. And I have 2 million bits per second times 2E8. That's how long I'm going to have to wait. 2 full packets in front of me in the buffer. There's 1 packet that's 50% transmitted, so it's 1/2 times a third. So it's a total of 2.5 packets. Tells me how big they are, how fast I'm going through them. This is the total number of bits standing in front of me. This is how many bits per second I can clear out. It's that simple. That's how long I'll wait. And you can generalize this as well if you want. It's basically a version of L over R, blah, 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 blah. So turn it in by, when do you want it due? Friday? By Friday, turn it in. I'll give you the solutions on Friday, so you'll have them to study. And I'll give you some extra problems to work on with the study guide. So you'll walk in. I'll go over the simulators you're going to have again. I'll show you a snapshot, like I showed you this table. I'll give you the tables that you're going to see, so you're not going to have to walk in and start reading, like, what do these columns mean? They'll be exactly the ones you've seen before. I'm not going to surprise you with pictures. I will ask you maybe to draw one of the traces. Like I have 4 packets in. It's parallel and it's non-persistent. Draw me what that looks like. And it'll make it simple. I want you to be able to draw. Or I'll give you 3 or 4 choices and you tell me which one it is. I might do that because it's a lot easier to grade. And it's harder to kind of figure it out sometimes. All right? You guys okay? All right. Have a great weekend. I will see you in here. We'll start class next time. It's a short test. We'll be done by halftime, and we'll have new lecture in the second half. So it's not just an exam for 3 hours. It'll be 60, 75 minutes. We'll take a break, and then we'll come back and have lecture. Okay? This will not be death by partial exam. All right, bye, everybody.